Hi, everyone. Thanks for joining us for today's reading group, everyone who's here in person and online. The topic of today's group is going to be optimal transport metrics, ways to approximately calculate these metrics, why optimal transport is good, and a couple of applications in machine learning that have really become popular over the last 4 or 5 years. So let's get started. I think before we talk about really get into the meat of the presentation, it's important to talk about why optimal transport is so popular these days and why it's like a nice natural framework to develop metric distances and discrepancy measures on. And it basically turns out that if you're in the business of comparing two probability measures, as long as they have some sort of underlying metric space, then optimal transport gives you sort of a nice geometry for comparing these probability measures. And it basically generalizes the idea of the shortest path principle. So if you have the ability to take 2 points in some space and calculate the shortest distance between these 2 points given some sort of cost function, then optimal transport ports this idea of shortest path to groups of points or distribution of points or continuous distributions on these points. And the nice thing is that if you have some sort of underlying metric space like a Euclidean distance and it gives you some nice properties, optimal transport will borrow these geometric properties and let you apply them for distributions. So for example, if you have a Euclidean metric that you're building an optimal transport space on, a Euclidean metric allows you to interpolate smoothly between 2 points in the space, and you can sort of get any point in between. It allows you to calculate weighted sums of points in the space. And if you apply optimal transport to such metrics, you end up with what's called a Wasserstein space, where you can naturally interpolate between probability distributions instead. So if you look at this example here on the left, if you have some sort of two-dimensional Gaussian on the left here and another two-dimensional Gaussian on the right here, if you want to smoothly interpolate between these two distributions, if you did it naively in the sense of L2 distance, where you just average between the two distributions, you'd end up with what looks like this weird bimodal distribution, because what you're really doing is you're averaging the probability mass of the two distributions. And that's not really a natural, in some ways it might be useful, but it's not really a natural way of thinking about how to interpolate between distributions. Whereas if you do this in the Wasserstein space, you end up with a nice notion of moving between two distributions. And then finally, the other nice thing about optimal transport metrics are they provide you a metric for probability measures that have non-overlapping support. And this is really important in a lot of applications, but I think the most obvious one is in generative modeling, where if you have some sort of high dimensional space for your data, and you have some small underlying latent space mu that you're taking samples from and then pushing forward through your generative model, you end up with this low dimensional manifold in this high D data space. And now, if you want to see how good this manifold fits your data distribution, you can't use something like maximum likelihood or Kullback-Leibler divergence, because this low dimensional manifold has basically non-overlapping support. It's zero almost everywhere. So you can't really take the KL divergence because it'd be undefined on points that don't lie in this manifold. And it's hard to create a manifold that touches each of the points in your training distribution. But with optimal transport, there really isn't any requirement for there to be overlapping support between two distributions that you're trying to compare. And there's also nice connections to other integrable probability metrics, such as maximum mean discrepancy and other like kernel-based distances like energy distance that you could interpolate to from Wasserstein spaces. So in this talk, what I'm going to focus first on is giving like a brief mathematical formulation of optimal transport theory and lead up to motivating Wasserstein distances, which is sort of the canonical metrics that are used when people think about optimal transport theory. And I'll show how Wasserstein distances are great, and they're really a nice way of comparing distributions. But then there are a lot of sort of computational and statistical issues in actually calculating Wasserstein distances. They have cubic scaling, they're not really differentiable. Their statistical properties of convergence get really bad when you look at high dimensional distributions, especially if you're trying to get an empirical estimate for the Wasserstein distance by sampling from two distributions. The convergence of this empirical distance to the true distance between the distributions actually scales really badly in high dimensions. And so then I'll spend some time talking about recent work over the last 4 or 5 years that looks at approximate or regularized optimal transport, which solves a lot of these issues. Specifically, I'll focus on sliced Wasserstein distances and Synchrons divergences. And these are sort of two of the main approaches that are out there for dealing with optimal transport in a nice, differentiable, scalable way that deep learning likes so much. Finally, I'll talk a bit about some applications of optimal transport in machine learning, and time permitting, a few extensions, such as what if you don't have conservation of mass between two probability measures? Could you still do optimal transport? And what if you don't have a common metric between two probability distributions? Can you still formulate an extension of optimal transport? And turns out in both these cases, you can get something that's quite useful. Right, so let's talk about the mathematical preliminaries. And it's nice to look at the mathematical formulation of OT from a historical perspective. So I'm going to talk first about the Monge problem. And so Monge was this French mathematician who in 1781 asked a very simple question, really, which was, if you have a pile of dirt, how do you move it to another spot while minimizing the effort it takes to move this pile of dirt, right? And it actually took over 150 years before someone could, concretely solve this and give ways of solving this. So it seems like a very trivial problem to ask, but it's actually quite difficult to formulate. And so to do this more concretely, let's say you have two probability measures, mu, which is defined on a space omega source, and nu, which is defined on a space omega target. And you have some sort of cost function that says, how much effort is it to move a point from mu of x to nu of y? And then you have some sort of push forward operator, where I use this formulation T hash to refer to a push forward operator that transfers measure from a space, from the first space to the second space. And what that means is that if you apply the push forward operator on mu of x, it moves the points to nu of t of x, right? And this push forward operator, at least in the way Monge formulated it, needs to conserve mass. And so what that means is, in terms of measure theory, if you have subsets A inside the target distribution, then for every subset A that you measure the measure nu on, there should be a pre-image of it in the original measure mu. So for every point that's shown up in mu, there needs to be a corresponding point that you moved mass from in mu. And what Monge said was that you want to find a mapping of this push forward operator that basically minimizes the integral of the cost of moving a point from x multiplied by the probability measure of that point x integrated over the entirety of the source space. And it's constrained to the requirement that t needs to be a push forward operator. Now, this is like a deceptively simple integral to solve, but it turns out that this has a lot of issues. And the first thing is that push forward of mu equals nu is not really a convex constraint. It's not easy to write it down in any sort of Lagrangian form and solve it out easily. You're not really guaranteed of the existence of a t for any two given measures. You're not guaranteed that if it does exist, it is unique. And the other biggest constraint here is that this push forward operator doesn't allow you to split mass. So if you have a point mu, or if you have a point x in the original measure mu, you can't really spread its mass around to multiple points in the new measure nu, because of the conservation of, because of the way this is formulated in its current form. So if you think about it, you can't really map a Dirac delta measure to a continuous measure, because if you plug in the Dirac, yeah.
Can I ask questions from here, or try to go to the microphone or something?
I think people will hear better if you're in front.
Okay.
Yeah.
Hi, my question is, why would we care about unicity or uniqueness of T? Because aren't we taking an infimum over the set of all? So is it important? Is that something we want?
Yeah, so you technically want the unicity of T to exist, because I guess you don't really need the unicity of T to exist in Monge's formulation, because you are taking the infimum of it. But I think what's also the issue is that the infimum isn't unique. So you could have multiple push forward operators that also map from mu to nu, at least in the Monge formulation. Like the number of constraints you have aren't enough to tell you that there's a unique solution to this.
Okay.
right? And so you can't really map Dirac delta masses to continuous measures, because if you plug it into the integral, you can really only push forward a Dirac mass to another Dirac mass. Now, in practice and machine learning, you really want to be able to compare empirical distributions with continuous distributions and vice versa. So this doesn't really work. And for the next 160 years almost, no one could really do anything about this until in 1942, a Russian mathematician by the name of Kantorovich came along, and he said that the constraints that you have for the Monge problem are really too difficult to solve, because you want a deterministic map between mu and nu, and that's not really feasible to solve in a lot of cases. So let's relax the requirement of these maps T from being deterministic to being a probabilistic coupling. And what that means is now for a point X in the original measure mu, you have a probability distribution in the measure nu where this point can go. And so now you can spread the mass of X around in the form of a probability distribution over nu. And so it allows you to split mass, it allows you to take multiple points from the original measure and send them to one point in the new measure and so on. And so you've relaxed this deterministic one-to-one mapping requirement to a probabilistic coupling between the original, the source space and the target space. And what a probabilistic coupling is it's basically a probability distribution over the joint of these two spaces. And it needs just a few constraints, which is that it needs to be positive. The marginal of this coupling over the target space should equal the original space. And the marginal of this coupling over the original space should include, should give you the target measure. And that's just conservation of mass in a different sense, saying that you can only really move the entirety of a measure from mu to the entirety of the measure to nu. So if you marginalize this coupling over mu and nu separately, you should get the original measure back, right? And turns out that there are a lot of couplings between any two measures in general that could satisfy these constraints, but there always exists at least one coupling, and that's the product coupling. So if you look at mu times v, that probability distribution satisfies these constraints, and it is a valid coupling. And so that's what the product coupling would look like for two one-dimensional distributions, mu and nu. You'd have this joint distribution over the space in the center here. But what this opened up the possibility was for sending a Dirac mass to two Dirac masses, or a Dirac mass to continuous distributions, and so on, because you can just define the coupling to be, one half and one half over here. And as long as it's a valid probability distribution, you're good. You don't need to worry about moving continuous distributions to discrete and vice versa. And so now what Kantorovich said, his primal formulation of optimal transport was that if you have these two measures, and you have the same cost function as before, find the infimum of the coupling that minimizes the same integral of the cost function times the coupling, such that the coupling lies in this set of distributions P. And this set of distributions P is all couplings that satisfy the marginality constraints. And this is a relaxation of the Monge problem, but it allows for mappings between arbitrary measures. And that's something that we care about. The problem here, though, is that if you actually try to solve this, the coupling is like a quadratically large term. It's of the size omega s times omega t, and you need to optimize for this somehow, given omega s plus omega t constraints, which are the two marginality constraints. And so there were a lot of people that came upon the same sort of relaxation and primal formulation of the problem. But what Kantorovich is really famous for is flipping this and calculating the dual to this problem. And so what Kantorovich said was that, can you do better than having to find a coupling that's of size omega s times omega t? And he said that it is possible to do better than that. You could, instead of optimizing overall couplings that satisfy these constraints, consider just two measurable functions, phi and psi, on the source measure and the target measure that are Lipschitz continuous. And what Lipschitz continuity means here is that if there's some sort of constant k that's greater than 0, then a distance on the image of f is upper bounded by k times the distance on the inputs x. So it's just a way of saying that these functions are smooth, the derivative does not change too quickly, and it's a continuous function. And what Kantorovich said was that instead of solving the primal formulation that you had before, you solve the dual form of it, which is to say that you want the maximum of the two functions phi and psi that satisfy this equation, which is that the integral of phi over the first measure plus the integral of psi over the second measure. You want to maximize that given that the sum of these two functions at any point is less than equal to the cost function. And I know this looks very different from the primal formulation, but the derivation is not very trivial. And it takes about 20-30 minutes to derive this. So I'm not actually going to do it in today's talk, but like suffice to say that this formulation is exactly equal to the primal formulation. And you can show it through just convex optimization ideas such as adding the Lagrangian of the previous constraints and then solving it out. But this is what Kantorovich won a Nobel Prize for, and it's a bit involved. So to show what this means in a graphical sense, let's consider two probability distributions, mu and nu here, the red and the blue distributions. If you solve the primal formulation of mapping mu to nu exactly, you'd end up with some sort of black curve here. That's the exact coupling gamma that maps mu to nu. On the flip side, what you could do is you could define two continuous functions phi, which is in the orange here, and psi, which is in the green here, such that the sum of these two functions at any given point is this brown curve here, and it's always upper bounded by the cost function, which is this curve in purple over here. And the equality where the sum of these two functions is equal to the cost function gives you exactly the same coupling that you had in the primal formulation. So basically these two ideas are equivalent, and you will want to maximize the dual formulation instead, given the constraint that the sum of these two functions is less than equal to C, and they will be satisfied at C. Yeah.
Sorry, I'm a little bit confused. How do you, given that you've solved this dual problem, you end up with two functions, phi and psi.
Yeah.
If I'm not mistaken, the solution to the primal problem is a joint distribution over the source and target space.
Yeah.
How would you recover the joint distribution given that you know phi and psi?
Yeah. So if you have solved for phi and psi, then maximize the dual formulation, then the points where phi of x plus psi of y equal the cost function x of y is where the coupling exists. And that's what the coupling is now. The trajectory of phi of x comma psi of y that satisfies that inequality. That trajectory is exactly the joint distribution of gamma. And so if you see it on the curve here, gamma over here looks like some sort of two-dimensional probability map. And the exact spot where this phi of x plus psi of y equals c of xy is satisfied is the same exact trajectory of the probability map.
So are you saying that gamma is only supported on this?
Yes. So in this case, gamma is only supported on that thin trajectory and nowhere else.
Right. And like, what is what is the value of gamma on that line, if you get what I mean? Does it just give the support of gamma, or does it also tell you?
Right. That's a good point.
The relative measure of different points.
Right. I think it also gives you the relative measure of the 2 points by basically integrating phi and psi separately over the 2 measures.
Okay.
And so you can get the value of gamma back from phi and psi. I don't know what the formulation is off the top of my head, but you can recover gamma given phi and psi and the trajectory on which they're supported with this inequality.
Okay, thank you.
Yeah. So it's now much easier to basically store 2 functions on omega s and omega t rather than just the coupling on a quadratically larger space. But you can do a bit better than this even. You could say that instead of optimizing over all possible phis and psis given the constraints, can we find the best psi given a family of functions phi? So this family of functions can be a neural network parameterized by some distributions or some like parameterized family of distributions. Given a family of distributions phi, can you find the best family psi? And so you want that given a phi, you need this function psi that satisfies this inequality. So you take it on the right-hand side. And so for all x and y, you have that psi of phi is less than equal to the right-hand side. So it also must hold that psi of y is less than equal to the infimum of the RHS for all x's, right? And this is just dealing with the inequality. If it's less than equal to the RHS for all values of x and y, it must also be equal for the infimum of the RHS for overall x's, right? So the smallest value that the RHS can take for some given x. And you basically take that term, the smallest value that the RHS can take for any given x, and you call that the C conjugate of phi. And this turns out to be basically like the best possible function psi that you can get given a phi. And that makes sense because this is like the most constrained form that psi can take given a family phi. It would be the infimum of the RHS over here. And so you can basically simplify the dual formulation now into a semi-dual formulation that only depends on one function phi. And so you replace the initial sum of integrals given the constraint to this dual formulation, which basically says that if you have a family of functions phi that have a defined C conjugate, then you just have to maximize this equation now, where it's the integral of phi over the first measure plus the integral of the conjugate of phi over the second measure, as long as phi has a C conjugate. And so, sorry. So depending on the use case, depending on whether we can get a nice closed form solution for the conjugate, the semi-dual formulation is sometimes used. But more often than not, people look at the dual formulation and try to solve it to basically get the optimal coupling between two probability measures, mu and nu. And so given all this mathematical machinery, let's finally talk about what Wasserstein distances are, because they're sort of like the canonical thing that's used in optimal transport theory. And we've really already defined them. So what the P Wasserstein distance is given an optimal transport coupling where the cost function is now specifically a distance metric, then the P Wasserstein distance is basically the infimum of the double integral of the cost function times the coupling for the coupling that satisfies optimal transport. So the coupling belongs to this distribution, this family of distributions P that satisfy the marginality constraints. And the infimum of this double integral over the cost function times the coupling is the Wasserstein distance between mu and nu. So you can think about this as taking the expectation of this distance metric if you're sampling points from the optimal coupling gamma between two measures. Or in dual formulation, you could say that if you have phi and psi to be smooth Lipschitz continuous functions, then you want to find the maximum of this double integral such that the sum of these two functions is always upper bounded by your distance metric d of p. And there's a special semi-dual formulation of this when p is equal to 1 and your cost function is just the L1 distance between 2 points. You could say then that, you can prove then that if the cost function is equal to the L1 distance, then the conjugate of phi is equal to minus phi for all phi's that are 1 Lipschitz. And you can think about this by the definition of the conjugate, which is the infimum of C minus phi. And so the infimum of mod of x minus y is basically 0, wherever x is equal to y. And so the infimum of the right-hand side in the previous slide would basically give you 0 minus phi, which is minus phi. So the conjugate of phi is minus phi for all functions that are 1 Lipschitz for this very specific cost function. And so then what the Wasserstein distance boils down to is the integral of phi over the first measure minus the integral of phi over the second measure. Then the phi then maximizes this integral. Yeah.
Sorry, question. So the 1 Lipschitz here is saying that the Lipschitz constant is bounded by 1.
Is bounded by 1, yes.
And this has nothing to do with the fact that you're using the L1 metric, right?
Yeah. Those are separate. So the functions need to be 1 Lipschitz, and you're using the L1 metric. So I guess, my bad. I used L_1 to refer to 1 Lipschitz, but I see how that can also refer to the L1.
Okay, and this, you're not necessarily considering when you say mod of x minus y, x and y could be multidimensional, right?
Yes,
just using the L1 metric.
Yeah, the L1 metric. X and y could be multidimensional. There's no other constraint on x and y, right? And so what the Wasserstein 1 distance then looks like is the maximum, like the function that maximizes this integral. And now this in general is very hard to solve exactly for arbitrary measures mu and nu. In machine learning, people do approximate solutions of this by assuming phi is a family of neural networks and then bounding the gradients or the weights of these neural networks to make them roughly one Lipschitz, and then solving the optimization problem to maximize this integral. But in general, there are better ways of solving these Wasserstein distances approximately than there are solving them exactly. For discrete measures, you can solve for Wasserstein distances using linear programming, basically, but that ends up with order cubic complexity to solve a linear program that gives you the exact Wasserstein distance between two measures. So the good thing now is, once you've gone through all this mathematical machinery and you've obtained what Wasserstein distances are, they end up being very natural metrics to compare between two probability distributions. And the thing is that they encode very different geometries from what you'd have if you were using standard information divergences, if you were using KL divergence or Euclidean distance or the Hellinger distance and so on. So on the left here is an example where you have a fixed one-dimensional Gaussian at sigma naught, m naught, and then you have another Gaussian at m and sigma, and you're moving m and sigma around where you're moving m in the x direction and you're moving sigma in the y direction, and you're plotting what these different distance metrics look like as a function of m and sigma. And so you can see that for the KL divergence, which is this plot here, and for the Berg distance, which is basically the reverse KL divergence over here, as you move to points of sigma that might result in singular matrices, the KL divergence starts blowing up or shooting down, right? And so in a way, KL divergence is good when you're comparing two Gaussian distributions if you really want to prevent singular matrices for your covariance function, because KL divergence would blow up a lot when you have covariances tending to singularity. But you might also not care about that so much, and you might want a distance metric that can handle arbitrary covariances a lot better. And it turns out that the Wasserstein 2 distance between two Gaussian distributions is basically just the Euclidean distance in terms of m minus m naught square plus sigma minus sigma naught square. So it's actually constant for all m's and sigmas that are a Euclidean distance away from the m and sigma of the Gaussian distribution. And so there might be cases where you want to have a distance metric between Gaussians that's described in this way, where you don't really care about covariances tending towards singularity causing your distance metric to blow up arbitrarily, and you want the distance metric to be roughly, to behave very stably as you change sigmas and m's. The other nice property that Wasserstein distances have is that, again, they borrow properties from the underlying distance metric. So if you're using the Euclidean distance to define your Wasserstein distance, then you end up with the ability to interpolate between distributions the way you could interpolate between points. You are able to calculate weighted sums of distributions in a meaningful way, what are known as barycenters. And so to give you an example, if you have these four two-dimensional distributions, a circle, a four-pointed star, five-pointed star, and a bimodal distribution, if you wanted to interpolate between our unimodal and a bimodal distribution using sort of the Euclidean barycenter, where you average over the two distributions, you'd end up with something that's not really meaningful because you're just averaging probability mass. So you'll have your interpolating distributions basically having mass from the unimodal distribution and mass from both modes. But the Wasserstein barycenter ends up looking like something that's a lot more geometrically meaningful, where if you interpolate between the unimodal and the bimodal, the mass actually splits and flows away to the bimodal distribution because you're solving this optimal transport problem. And in practice, there's been a lot of work using this in computer graphics and vision, where you represent 3D shapes as point clouds, and you can smoothly interpolate between different 3D shapes by basically just calculating the optimal transport mapping between shapes. Right. So at this point, it's good to say that Wasserstein distances look like they have really nice properties for comparing distributions. They solve this optimal transport problem. But what's the catch here? Right? Because if you could do this for any probability measure, especially for measures that have non-overlapping support, you'd want to do this. But the catch here is that exact Wasserstein distances are really expensive to calculate in practice. They're not differentiable generally, so you can't really plug them into deep learning machinery and AutoDiff software and use them as components for some sort of AutoDiff program. And then the statistical properties don't scale to very high dimensional distributions. So I'll get to that last point in a bit. But I want to show what these issues are for a concrete example. And so let's talk about optimal transport for two discrete distributions. So let's say you have a discrete measure mu, which is just a sum of Dirac delta masses with some weights ai, another with sum of Dirac delta masses with weights bj. The only requirement you have that the ai's and bj's sum to 1. And you can consider, you can either consider point clouds where these weights are uniform, and so all these points have equal weight, and you're just trying to map between one cloud of points to another cloud of points. Or you have histograms where the positions xi and yj are constant, but now you're just trying to map the different weights of the histogram from one to the other, right? So if you convert the optimal transport problem now to this discrete formulation, you'll have a cost matrix, C of xi and yj, which just gives you the pairwise cost between each xi point and yj point. And the optimal coupling between these two measures is now given in this discrete form as basically the norm between the cost matrix and the coupling then minimizes this norm, right? This is the same, you convert the integral overall couplings to a double sum now. And you want to find the coupling that minimizes this double sum, given the constraints that these couplings should still marginalize to the respective distributions of A and B. Now, this thing you can actually concretely solve using linear programming. You have n into m variables, and you have n plus m constraints. The n plus m constraints here are that the gamma i's, if you sum across the row, should equal 1. The gamma j's, if you sum across the columns, should equal b. And then for all gamma I, comma j, you want to find the optimum. Now, you could flip this around in the dual formulation where you're trying to find two weight vectors alpha and beta, which are now the analogs of the two functions phi and psi. You want to find the maximum of alpha transpose A plus beta transpose B, given the constraint that the sum of the alpha i's and beta j's should be less than the cost function. And this is exactly just flipping from the primal formulation to the dual formulation in discrete form. And so this results in n plus m variables instead and n into m constraints instead, because now the variables are the terms of alpha, the terms of beta, and the constraints are that for each alpha ij pair, their sum should be less than equal to the cost function ij here. And so you can solve this using linear programming. But now the thing with linear programming is that it's hard to find unique solutions. Linear programming tends to be quite unstable. It tends to be quite dense to figure out exactly what solution you have. And if the solution is stable, if you slightly modify the values of C, if you slightly modify the weights A and B. And that's usually represented in the form of all possible family of solutions lie on this convex polytope of P, and then you have some direction that your cost matrix takes, and you want to find the shortest perpendicular distance to this cost matrix that lies in the convex polytope. So if you wiggle around the values for C, then you could end up with an entire edge of this polytope being your solution, or you could flip from one point to another point quite easily. And so it's quite unstable. And also, if you calculate the solution using linear programming, it's not differentiable at all in general. It's definitely not parallelizable on GPU hardware, and so it doesn't scale well to a large number of points. And it turns out that solving a linear problem is basically higher than cubic complexity, which is really bad if you have any meaningful number of discrete points n and m, right? So you'd have cubic times log n plus m, which is really quite intractable for most applications.
Sorry, it's cubic or quadratic?
It's cubic because it's n plus m times n times m. So that ends up being cubic in terms of, the max of n and m.
Thanks.
Yeah. And so now let's also consider what happens if you don't really know your underlying measures mu and nu, but you're trying to find an empirical estimate of the Washerstein distance by taking samples from mu and nu and calculating, the Washerstein distance between these empirical distributions instead. Can you say something about what the statistical convergence of the Washerstein of this empirical distribution would look like compared to the Washerstein over what the original underlying distribution is? And it turns out that there is a way of quantifying this for d greater than 3 and if your metric space is RD. And it turns out that this bound is actually quite bad because it scales to 1 over D. And so what that means is, if the dimensionality of D is 1, then you need an order of n points to have, like a linear bound. But now let's say D is equal to 10, you would need an order of n to the 10 samples from your underlying distributions to actually converge to the true Wasserstein distance over the underlying distributions. So what actually ends up happening is that the Wasserstein distance of your empirical distributions is in practice very far from the Wasserstein over what the true underlying distribution should look like. And this scales with 1 over 2, which is again quite intractable. And so what we would like for machine learning applications is to have a method that's faster, scalable, differentiable, ideally through autodiff, and have better statistical convergence properties. So if we have a way of approximating a distance between two underlying distributions, and the empirical distribution should also tend to this. And that brings me to the other part of the talk, which is talking about a lot of work that's happened in the last 4 or 5 years on finding ways to approximate the optimal transport problem or regularize the optimal transport problem so that you can get faster methods to calculate it approximately with better statistical convergence. So these methods don't solve optimal transport anymore, but they almost solve optimal transport. They approximately solve optimal transport. And in a lot of cases, the solutions that they have look very similar to the optimal transport solution, but with slightly worse mappings. And so the first method that I want to talk about are called sliced Wasserstein distances. And they rely on this property that if you're in one dimension, so if you're comparing measures of singular dimensions, the Wasserstein P distance between these two one-dimensional distributions is just a function of the inverse of the cumulative distribution. So it's a function of n inverse mu and f inverse nu. And the integral would basically look something like that. And there is a proof to this, but it doesn't really matter what the exact form of the integral looks like. But sort of in a graphical way, if you think about this, if you have two 1D distributions and their corresponding cumulative distributions given by f mu and f nu, you can take the inverse of these, which in this one-dimensional case is the same as flipping across x equals y. And then the Wasserstein 1 distance would basically be the sum of differences between f inverse nu and f inverse mu. So the sum of the differences in this area bounded by the two curves. And the Wasserstein P distance would basically be the sum of the pth powers of the differences in space between these two curves, right? And it turns out that for discrete distributions, the 1D Wasserstein P distance can be calculated in order n log n times. There's been a lot of work to basically find really fast algorithms that can take these cumulative distributions, invert them, and calculate the distances very fast. And so the idea of sliced Wasserstein distances are to take whatever high dimensional distribution you have and project them onto one dimension, project them into make multiple projections of them into one dimension, calculate the 1D Wasserstein P distances instead, and see if you can approximate the high dimensional Wasserstein P distance by these 1D Wasserstein P distances. Or even if you can't approximate them, use this like average of the 1D Wasserstein P distances instead to compare your two distributions, because calculating the actual high dimensional Wasserstein distance is very intractable, right? And there was a lot of work by Bonil et al. And Kaluri that accomplished this using the radon transform. So the radon transform is this transformation that's quite popular in medical imaging. CT machines work using the radon transform, but what it effectively is you project your d-dimensional distribution into one dimension by basically slicing a d-1 size hyperplane through the distribution and then taking the line integral through that. So for this two-dimensional example here, you take one specific line through this two-dimensional distribution, and that becomes your projected 1D distribution of the 2D distribution. And you can basically take different directions of projection, and that gives you different projections of your high dimensional distribution. So in general, if you have a d-dimensional distribution, then you're sampling this unit vector of directions theta through on a d-1 sized unit sphere. And yeah, so that's what the radon transform gives you. It gives you a way of sampling a d-1 sized unit vector and then projecting your distribution along that unit vector by taking the integral. And so you can approximate your high dimensional distribution by taking these projections instead. So what Bonil et al. Suggested was something called the piecewise Wasserstein distance, where they said, we can't really take the Wasserstein distance in this high dimensional space, but what we could do is we could project the high dimensional distribution mu and nu using a radon transform and calculate the 1D Wasserstein P distance instead. And then you can basically take the integral over all possible projections that are possible for every single unit vector that you can sample in this unit hypersphere, right? But obviously this is also intractable in practice because you can't really take this integral over all possible directions of the unit vector. So they end up approximating this using an MC estimate where they just take k possible projections and then they average over it to give some approximation of the Wasserstein P distance in high dimensions by a sum of Wasserstein distances in one dimension. And each one-dimensional calculation is n log n, and then you're doing k samples of this. So the computational complexity of this is actually k times n log n, which again is a lot better than the cubic complexity that the linear programming optimal transport solution had. And there was very recent work by Najahi et al. That showed that taking these sliced Wasserstein distances, they're actually true metrics, and the space that they impose upon the two distributions are topologically equivalent to the high dimensional Wasserstein P distance. And a lot of this work is very theoretical and very mathematical, but what it boils down to is saying that you end up with a lot of the same properties that a high dimensional Wasserstein space would have if you take this sliced Wasserstein distance instead. They are weaker properties, like functions tend to converge more slowly in the sliced Wasserstein space compared to the original space, but they are still topologically equivalent. So you can still interpolate between distributions using the sliced distance. You can still calculate barycenters, etc. The statistical convergence of the sliced distance between two distributions to the two empirical samples from it is actually 1 over square root k because of the Monte Carlo step times 1 over square root n. So it ends up actually being independent of the dimension of your underlying distributions d. The trade-off is that as d gets higher and higher, your sliced Wasserstein space ends up looking worse and worse compared to the original Wasserstein space. But you can sort of improve how much worse they look compared to the original Wasserstein space by generalizing the idea of a radon transform. So instead of taking a sliced hyperplane through your space and integrating over that, you can take sort of some generalized parametrized transform, some generalized parametrized hyper curve that's parameterized by some neural network and integrate over that. And this work by Kalori in 2020 showed that this actually makes your sliced Wasserstein distance a lot closer to the original high dimensional Wasserstein P distance. But there's still some issues here in that it's not really differentiable in practice, and it can require a very large number of MC estimates to converge to a good solution, especially if you're sampling in a very high dimensional space, right? So you want a way of dealing with these issues, and that's what the second camp of current research comes into, which is by regularizing the optimal transport problem. And so the idea of optimal transport with regularization is you're saying that the exact coupling between two distributions is very hard to solve exactly, but can you roughly solve for them given some regularizing terms on the components of this optimization problem? So the first option is you could add a bunch of priors to the family of couplings that you're considering. You could say that you no longer want to consider just the exact coupling. You want to consider the coupling plus some wiggle room that's defined by some regularization term R over here. So Kuturi suggested in 2013 the idea of entropic regularization, where you minimize the optimal transport problem, but you also add the entropy of the coupling distribution, and the regularization term is that the entropy of this distribution needs to be high. And so now this no longer will look like that one very tight almost deterministic looking coupling between two distributions, you're now giving it a lot more wiggle room to say that you can approximately map masses to each other, but as long as the entropy isn't too high and the optimal transport problem is roughly matched, you're still fine. And then there are other ways of
Sorry, are you changing the cost function that you're trying to minimize, or
yes.
Are you changing the constraint that it has to satisfy?
You're changing the cost function that it needs to minimize. Okay. So the original cost function has the constraints inherently within it.
Okay.
But now the cost function itself is the original one with the constraints plus a regularization term. And that's the new cost function to minimize.
Right, so you don't actually need to have the marginals matching.
Yeah, you need them to now roughly match in a
okay.
sense.
All right, thanks.
Yeah.
Can I also ask a question?
Yeah, go on.
Thanks. So maybe I missed this, but what's the motivation for doing optimal transport? Like, for regularized optimal transport, is it like easier to compute?
Yeah. So basically, compared to the cubic linear programming solution, I'll show in a bit that regularized optimal transport is a strongly convex problem that has quadratic scaling and much better statistical convergence. The idea being that the exact optimal transport problem is very constrained and very hard to solve. But if you regularize it, you can end up with like approximate solutions that are quite quick to calculate and then are generally differentiable and converge better.
Nice, thanks.
Yeah. And so I'll skip over the other options to sort of regularize it, because I'm going to focus on one very specific form, which is the entropic regularization, where you're adding this entropy term to the cost function initially. So let's talk about that. So now, instead of minimizing the original cost function with the constraints, you're minimizing that plus this regularization term. And actually, Andrew, to clarify, you still need the constraints that the marginals are equal to the original distributions to be true. That constraint still needs to be satisfied. But now it needs to be satisfied along with minimizing a different cost functional instead. So you end up with couplings that still marginalize to the correct distributions, but they no longer exactly minimize the map. They might roughly minimize the map, right? So you still need those constraints. And so, for example, you can define something that's called a regularized Washerstein distance, which again is like the minimum of the optimal transport problem minus lambda times the entropy of the coupling. And so you can see here in this graph, if you have a distribution mu and a distribution nu, on the very left is the optimal transport solution. And it's actually this hyper constrained, very sparse solution. It's very hard to make out on this plot, but it's basically this almost like one-to-one mapping between mu and nu that exactly maps between the two. But this is a very sparse matrix because, again, it's the solution to a linear programming problem with n plus m constraints that'll have at most n plus m non-zero values. But as you start adding regularization to this, the family of couplings that are allowed become more and less constrained and easier to find. And conceptually, if you take this all the way to the end, you end up with like the maximum entropy distribution that still satisfies the constraints, which ends up being the product coupling again of mu and nu, because that is the coupling that has the highest entropy that still marginalizes to the correct values. What happens is that if lambda is greater than 0, because entropy is a strongly concave function, this new optimization term becomes a lambda strongly convex optimization problem. And there's a lot of work showing that this is true in general for any definition of a Wasserstein P distance. If you add the entropy, if you subtract the entropy from the optimization, from the optimal transport task, then it ends up being a strongly convex optimization problem, which means that there are fast and scalable differentiable methods to calculate the optimal solution now for this regularized problem, which ends up being quadratic complexity in general. And there's ways to improve that if you're using convolutions on specific spaces. And there's been a lot of work in computer graphics to improve this bound, but it's order quadratic in general. This also has better statistical convergence. This regularized distance has better statistical convergence compared to the unregularized but exact Washerstein distance. So I'm going to briefly talk about what this algorithm looks like. And this algorithm, Synchrons Algorithm, it follows from this proposition that says, if you have an optimal coupling that minimizes the optimal transport minus lambda times the entropy term, then there exists two vectors u and v in the source space and the target, in the source measure and the target measure, such that the optimal solution looks like a diagonal matrix times k times another diagonal matrix, where the k here looks a lot like a kernel matrix. It's basically the pointwise exponent of the cost function divided by lambda. This isn't that difficult to prove. You could basically write the convex optimization problem in terms of its Lagrangians. You could say, you have the inner product between the couplings and the cost function plus the minus the entropy term plus the constraint that gamma marginalizes to A plus the constraint that gamma marginalizes to B with respect to the other measure. And then you take the derivative of this with respect to gamma ij and you set it to 0. And this ends up with like solutions of the form that look like this, which basically result in the proposition above. So that proposition isn't hard to prove. Then if you know that this proposition holds true, how do you solve this? The easiest way to begin solving this optimization task is to basically solve the marginal constraints first. So you say that this optimal coupling times the unit vector in the source in the target space should give you the source measure and vice versa. And now a diagonal matrix times the unit vector just gives you the vector, and a diagonal vector times another vector here basically gives you the piecewise multiplication of the two vectors. So you end up with u piecewise multiplied with kv equals A, and v piecewise multiplied with k transpose u gives you B. Right. And in general, that ends up being a fixed point iteration algorithm that exactly solves this and converges to the true solution. So what you can do is you can basically fix the value of v, initialize it randomly, solve for one step for u, fix the value of u, solve for v, and so on and so forth. And this converges, and that was shown by Sinkhorn in 1967, and which is why this algorithm is named Synchrons Algorithm. And so now you have this fixed point algorithm that can basically give you u and v, using which you can calculate the optimal regularized coupling lambda. You can define something that's called the iterative Washerstein distance, which just uses the nth best approximation to the optimal regularized coupling. So if you know what the optimal gamma is in the nth step of the iteration, the iterative Washerstein distance would just be the inner product of this optimal coupling with the cost function, because this is the coupling that's minimizing that inner product, right? And it ends up that since all you're really doing are matrix vector products, the only non-linearity you have here is really the piecewise division. This is very easy to do in an auto-differentiable way. You can set up some sort of auto-diff software that takes in points xi's and points yj's, two weight matrices, you calculate the cost matrix C, which gives you this kernel matrix K, and then all you're doing are matrix vector products, passing them through a non-linearity, which is the piecewise division, more matrix vector products, another piecewise division, and this iteratively, which you can, unroll out. And so the nice thing now is that AutoDiff software can basically give you the derivatives of this iterative Wasserstein distance with respect to any of the quantities that you might want to take gradients with respect to. So you might want to wiggle around the points xi's and yj's and still find a distance. So you might want to wiggle around the weights a's and b's that weigh these points and still find what the Wasserstein distance would be. Or you want to optimize the weights or optimize the locations of the points. This algorithm ends up having quadratic complexity times quadratic complexity in terms of the dimensionality of the space. So this is something to be aware of because you're doing matrix vector products. These matrix vector products depend on the dimensionality of your underlying measures. That is a factor that can come into play, where if your dimensionality is too high, then it becomes hard to scale, but it's still a lot better than exact Wasserstein distance. And then Sinkhorn also proved that U and V have a linear convergence rate to the optimal solution, but that linear convergence rate is upper bounded by lambda. And what can happen is if the value of lambda is too high, then your convergence can slow down a bit. Even though it's technically linear, the rate can become very slow. But in practice, for like small values of lambda, this converges pretty fast to the optimal solution as well. So let's talk about what we do now that we have this Synchrons divergence, this Synchrons algorithm for getting a regularized form of the Wasserstein distance. The issue here is that you can't really use this as a divergence metric because this regularized distance isn't really zero for comparing a measure with itself. And this is like one of the properties that you need for a divergence to exist. And the solution for that is very simple, and it was proposed by Ramdas in 2017. They call this a Synchrons divergence. And all they're doing is really they're subtracting from the regularized Wasserstein distance, the measure of the distance with itself and the measure of the target measure with itself. And this ends up being a divergence because it satisfies all the properties that a divergence would satisfy. And it's also nice because this formulation, the Synchrons divergence, has some really nice distance-based and interpolating properties. So when you take lambda equals to 0, so you start reducing the value of lambda to 0, you get closer and closer to the hyper-constrained exact optimal transport solution. If you take lambda to infinity, what you end up obtaining is basically maximum mean discrepancy, which is another really common and popular integrable probability metric for comparing distributions with non-overlapping supports. So what maximum mean discrepancy does is it projects all your points into some common space, which is usually like an RKHS space, and then it just takes the mean of the projections of these points and uses that as the comparison between two measures. Right. So if you take the limit of lambda tending to infinity, this distance boils down to this formulation here, which can be shown as exactly equal to what maximum mean discrepancy is in the space of the outer product of A and B. So if you replace this form of E back into this equation and change it around, you'll basically end up with the L2 norm in this AB space, right? So you can recover maximum mean discrepancy exactly as you take lambda to infinity. So what ends up happening is that Synchrons divergences basically create regularized spaces that smoothly interpolate from, in one direction, the exact Wasserstein space that has all these nice interpolating and barycentric properties, all the way to the very end where you have maximum mean discrepancy, which just is a quadratic cost operation that's just projecting these points and taking the mean between two clouds. And so by changing the value of lambda, you can decide how much of the Wassersteinness of the space you want and how much of the regular like Euclidean L2 distance of the space you want. And so let's go back to the statistical convergence issue that we had before, where trying to find the distance of the empirical distributions doesn't really converge to the distance on the actual distributions. On one end, you have exact Wasserstein distance with its cubic cost and 1 over n to the power 1 over d convergence, which is terrible. On the other end, you have maximum mean discrepancy, which is quadratic in costs. And the MMD paper shows that the MMD between empirical distributions converges to the MMD between the true underlying distributions with 1 over root n, which is it's quite a good convergence rate as they go. And then somewhere in the middle, you have Synchrons divergences that basically have order quadratic cost, with the caveat being that this d square term also exists. So for very high dimensional distributions, it might blow up. And the statistical convergence is also roughly of the order 1 over root n, weighed by this lambda term that does depend on the dimensionality of the problem. So if lambda gets too small, then it doesn't statistically converge. But if lambda gets too large, it doesn't maintain its Wasserstein nature anymore. So you have this nice way of like trading off between exact optimal transport spaces and MMD spaces through Synchrons divergences. And so given now this way we have of calculating approximate or regularized Wasserstein distances between measures, we can look at like some applications in machine learning. Like you can think of a lot of cases where you have a reason to get some sort of distance metric or measure between two distributions, and you want to minimize that or maximize that or use that to gain some insight into the problem, right? And by using the regularized or approximate forms of Wasserstein distances, you can actually have a lot of applications. So very quickly talk about like a supervised learning example where in 2015, Frogner and all basically said that you could convert multi-class classifications. If you have an input space X of images or something, and you have multiple labels that you're trying to classify them to through some neural network H of theta, you could convert this into an optimal transport problem where you could say that the output of your neural network H theta and your labels for the problem Y both lie on the k-dimensional simplex, right? And if you have some sort of cost matrix that measures some property on this KD simplex, you can solve for the Washerstein distance and use that to gain your optimal parameters theta. The problem is that the actual Washerstein distance doesn't differentiate, so you can't do it, but you can solve for the entropic regularized Washerstein distance instead. And so you just minimize this with respect to theta. And the nice thing here is that this cost matrix that you have, D of, this cost matrix is measuring some property between two KD simplexes, right? In regular supervised learning, you don't really have a way of specifying one class being more semantically similar to another class or one class being closer to another class in terms of labels. But in this formulation of supervised learning, you can, by setting this metric, this cost metric on the KD simplex to be something that measures semantic similarity. So you could make it so that the task of classifying between two breeds of dog is a very different formulation from classifying dogs versus cats and so on. And if you look at like large scale image classification tasks, such as the Flickr data set, they have a lot of these labels that somewhat overlap, that have similar semantic meanings, but you're still trying to classify them separately. And supervised learning can struggle a bit because you have a large number of classes with no idea what the relationship between these classes are. But what this paper does is they basically take these labels, they take the word-to-vec embeddings of these labels, and then the cost matrix becomes the Euclidean distance in the word-to-vec space. And they use that distance metric along with minimizing the regularized Wasserstein distance to train a multi-label classification task. And it ends up being that if you encode the semantic similarity between classes in this way, you end up with a much better AUC for performance compared to just a regular KL divergence or maximum likelihood setup. And in practice, they use like a weighted sum of the Wasserstein loss plus the KL divergence loss, and they have like an optimum value for alpha for which the AUC is maximized. So this is like one possible application where this idea of Wassersteinizing or measuring the Wasserstein distance between distributions can come into use if you have like semantic similarities that you can encode into the problem. The other more common use for optimal transport in the last few years has been for generative modeling, where I mentioned before, the issue with generative modeling is that you have non-overlapping support between the pushed forward generative distribution and your underlying data distribution. But with optimal transport and with Wasserstein distances, that's no longer an issue. You can easily measure discrepancy between measures with non-overlapping support. So let's consider P of R to be the empirical data distribution over your image space or word space, any like input space that you're dealing with that's equipped with some sort of metric. Z is the random variable over a much smaller latent space that you usually sample from, which is uniform or Gaussian, one of those. And then P theta is the distribution over the push forward of your latent space through the generator of your generative modeling application, so which is parameterized by theta. And now you can say, and this is what the Wasserstein GAN paper does, is you can train this generator G of theta by minimizing the Wasserstein 1 distance between PR and P theta. And so let's work through how they exactly do this. So the Wasserstein 1 distance, as defined before, is going to be the infimum of this expectation of the L1 norm between X and Y over the optimal coupling that satisfies the optimal transport problem. This is obviously a bit hard to actually solve in practice, but you can use the semi-dual formulation here because they're using the Wasserstein 1 distance. So as long as F is a 1 Lipschitz function, the conjugate of F is minus F. And so this problem simplifies to, in the dual formulation, looking like finding the value of finding the specific function F that is 1 Lipschitz that maximizes the expectation of F with respect to your real data distribution minus the expectation of f with respect to your generated data distribution. So your generator distribution. Right, and now the issue here is that obviously making f one Lipschitz isn't easy, especially as f is your discriminator or critic model that's again parameterized by a neural net. And so you can relax this condition to say, let's consider k Lipschitz bounded functions instead of one Lipschitz bounded functions. And the WGAN paper shows that if you do that, then, and if you replace that constraint of one Lipschitzness with k Lipschitzness, you end up recovering something that's a constant times the Wasserstein one distance. And there's a proof of this in the paper. I won't go into too much details of that, but if you relax this constraint, you end up with something that recovers constant times the Wasserstein one distance. So now that you have that, you can basically parameterize your family of functions f. And this, you can consider this as the discriminator model or the critic model in regular adversarial training of GANs. And you say that these functions are k Lipschitz. You solve for this maximization problem instead, where this is an optimization task now where you're optimizing over phi using stochastic gradient descent or any other algorithm. You're optimizing phi to maximize this expectation of f of x minus the expectation of f of the generated push forward of your latent distribution, right? And the other really nice thing that this paper proves is that one is that the distance you get is a multiplicative factor of the Wasserstein one distance. And the other thing that they prove and they solve for is this gradient of this Wasserstein distance with respect to theta, which if you think about it, you need some way of improving your generator model by minimizing your Wasserstein one distance. And the paper solves for what the gradient of the Wasserstein distance would look like with respect to theta. And it ends up being pretty simple. It's just the expectation over your latent space of the gradient of f of the push forward with respect to theta. And so all these terms are now tractable. What you can do is you can run like a min-max optimization scheme where you take one step to maximize the distance in this term here. You take one step to minimize it with respect to, you take one step to maximize this expectation term on the right here to get the Wasserstein distance, and then you take one step to minimize the Wasserstein distance with respect to the generator, right? And the way they bound these family of functions to be k Lipschitz is, this is where like this satisfaction of using Wasserstein distances kind of breaks down, because the way they bound these functions to be k Lipschitz is by clipping the gradients of phi. And so that makes sense, because if you think about Lipschitz continuity, all that is saying is that f of x minus f of phi is less than k times x minus y for a function f, like with the norms. And so the gradient in a sense is bounded by k. And so they roughly enforce this by clipping the gradients of the function to make it roughly k Lipschitz. And the nice thing that they show is that all these vanishing gradient issues that you have in adversarial training for regular GANs, they disappear because your gradient with respect to the Wasserstein distance is always well-defined and roughly linear and behaves really well across a large range of values for the real data and generated data samples. And in terms of what these look like, the fidelity of these images, they end up looking a lot better than adversarial training of GANs, at least in 2017. And you can obviously extend this idea by playing around with how you're enforcing one Lipschitzness or k Lipschitzness of your discriminator or critic. And so improved WGAN basically replaces weight clipping by exactly constraining the norm of your discriminator model to be equal to 1. And so if the norm of your gradient of f is equal to 1, then it's 1 Lipschitz by the definition of Lipschitz continuity. So they just do this explicitly by adding a regularization term that enforces the norm of the gradients of f to be equal to 1. And they show that this works a lot better than WGAN in practice, because what ends up happening with weight clipping is it really reduces the capacity of what your discriminator can discriminate, because this is obviously not as rich of a function space as you would want it to be. And so it finds it hard to actually discriminate between really complex multimodal distributions. But by just giving like a rough regularization of the norm of the gradients, you don't lose that much complexity. You don't lose that much capacity of your discriminator model. And so the improved WGAN training process works a lot better. And in the original WGAN paper, they have this issue where because you're clipping the weights, your weights end up having this very degenerate bimodal distribution where they concentrate to very specific values, because that's all it needs really to satisfy weight clipping. But by enforcing this norm, constraint on the norm, you end up with weight distributions that look a lot more meaningful, right? And then finally, we had this entire Synchrons algorithm and Synchrons divergences that just directly give you the gradients of the Washerstein distance with respect to any parameter you can think about. And so you can directly use Synchrons divergences instead of this very specific Washerstein 1 distance. And that's what the GANs with Synchrons Divergences paper does in 2017, where again, they define the empirical data distribution, they define P theta, and the generator is now trained through minimizing the Synchrons divergence between PR and P theta, where the Synchrons divergence is just in this form, it's just functions of the form of the regularized Wasserstein distance. So this is no longer minimizing the exact Wasserstein distance the way WGAN was. It's minimizing the regularized Wasserstein distance instead. And then you could just use a simple cost function where you could do, the L1 norm, the L2 norm, or whatever. But in this paper, they end up using a cost function that is another parameterized family of functions. This is, again, similar to like the discriminator term, where now they say that your cost function is just a neural network that projects your points into some p-dimensional space, and then the Euclidean norm through that, right? And that's what the model sort of looks like, where you have this generator, you have the generator that takes in latent samples and produces fake images. You have your input data to compare with. You use this neural network phi to project these points into some space, and then you take the cost in the space. And then you use the Sinkhorn operator, you use the Synchrons algorithm to gain a regularized Wasserstein distance. And the nice thing is you can now just auto-diff through this process and optimize for theta and phi, right? So in general, like being able to replace any comparison between two probability measures with a differentiable scalable algorithm that is very close to the exact optimal transport problem is a nice thing to have. And this is being used a lot to augment standard methods that exist out there. You could do variational inference by using Washerstein distance instead of KL divergence. You could create Washerstein gradient flows where you're now creating flows from one distribution to the other in the Washerstein space. And there's like a lot more applications where as long as all you're trying to do is measure between two distributions, if you replace it with Wasserstein, you get another algorithm that works really well. And that has non-overlapping, that doesn't have this issue of non-overlapping support. So in the last 5 minutes or so, I'm just going to very briefly talk about ways to extend optimal transport if you have the very strict constraints of optimal transport not being met. And this can happen in practice. So for example, if you have a case where optimal transport is not balanced, you don't have a normalized probability measure that you're pushing from to another normalized probability measure, and it's unbalanced. You have an unnormalized measure on the other side. You could think about like semantic segmentation where you're trying to map an image and labels to like the pixel values at each location. And there's no reason why all of these need to be normalized probability measures. As long as they're non-negative measures, can you augment optimal transport in some way to get a solution that works really well? You could think about like matching words in documents that have different lengths. So the embedding could be of different lengths, and they no longer are normalized. And so turns out you can actually do this. And there's been a lot of recent work over the last 2 or 3 years to like create unbalanced optimal transport solutions. And there's like multiple approaches that people have taken. So you can do a variational formulation of optimal transport, or you could think about adding an infinite source or sink somewhere in your problem that's just creating mass or eating up mass. But the variational formulation ends up with something that's like a bit easier to understand. So Matthias et al. In 2016, what they say is that if you have two measures that are just non-negative, mu and nu. You pick a mass that's upper bounded by the minimum of the two. So that's just saying you pick an amount of mass that's less than the total mass that's available between mu and nu. So if you're moving all the mass from mu to nu, you can't create any more mass than that. Or if nu only has a certain amount of mass, you can't move more of that from mu. So this m is upper bounded by the minimum of the two masses. And then again, you define gamma as the optimal coupling that satisfies, like the two marginal integrals of gamma. So gamma t is like the marginal with respect to the target space, and gamma s is the marginal with respect to the source space. And then you solve the optimal transport problem. But now the constraints are no longer that the marginals need to be exact. The constraints are now changed to say that the marginal of t just needs to be less than equal to mu. The marginal of with respect to s just needs to be less than equal to nu. And this coupling contains the same amount of mass as m that you've picked above here. So this formulation is, changing the optimal transport constraints to constraints that are a bit more relaxed, where now these marginals don't need to match exactly. But as long as an amount m of mass has moved from mu and nu using this coupling, as long as the coupling's marginalized to m, you're fine, right? And it turns out that actually solving this it's quite complicated and takes a lot of effort and a lot of like different fields of maths, and it's not really easy to formulate, but the solution ends up looking like something that's intuitive to understand, if not to prove. And that solution ends up being something that's called the Wasserstein Fisher-Rao distance, where you basically change the Wasserstein distance, which would be the Wasserstein distance itself would be the minimum value of gamma that optimizes this integral of the cost with respect to the couplings. You add these, you end up with these two extra terms to the Wasserstein distance if you want to solve this variational problem above. And these two terms end up looking like something that's quite intuitive to understand. Like you want a coupling that solves this optimal transport, but the masses are no longer the same. So now you just want the marginal of this coupling with respect to mu to be minimized using KL divergence, and you want the marginal with respect to S to be minimized to the marginal of mu. And it's hard to prove this, but the solution ends up looking very intuitive, and it's something that you can think about that makes sense. You would want to add these two constraints where you minimize the KL of the marginals to the distributions that you want while solving optimal transport. And it ends up being that there's a way of regularizing this by adding the entropy of gamma, and it gives you Sinkhorn iterations and Synchrons algorithm again in a slightly different form. And Pair et al. In 2017 showed that there's a general algorithm using the same Sinkhorn algorithm machinery that you could use to solve unbalanced optimal transport. And then super quickly, the very last thing that I'll cover is this idea of doing optimal transport between two very different metric spaces. So right now we were talking about spaces that shared an underlying metric where you could have this cost function that always associated a point X with Y. So optimal transport doesn't necessarily need that, but the definition of a Washerstein distance needed that. You need the ability to measure a distance between a point in mu and a point in nu in some sort of distance metric. But what happens if you don't have a way of measuring a distance between a point in mu and a point in nu? Or what happens if the dimensionality of omega s and omega t are very different? Can you still formulate optimal transport in some sort of way? And it turns out that you can extend optimal transport to measures that don't have a common ground space. And in 2011, Memoli proposed something that was called the Gromov Wasserstein Distance. It's got this somewhat icky form, but I'll try to simplify this with this example. So what the Gromov Wasserstein Distance does now is it says you don't really have a way of measuring a distance between a point I in the red space and a point J in the blue space. But what you do know is that the red space contains a metric. It's a metric space. The blue space contains a metric. It's a metric space. So you can calculate a distance between 2 points I and K in the original metric space. You can calculate a distance between points J and L in the second metric space. And these are going to be real valued functions because these are metrics. So now you can define some loss function between these two distances in the two different metric spaces. And the idea is that you're sort of saying, if you have 2 points that are semantically similar, that have been mapped to a new space with semantic similarity. So one possible way you could think about this is if you have one space that is made up of 3D shapes, 3D point clouds, and you have another space which is like the 2D projection of these 3D shapes into an image. So if you have a way of measuring the distance between the tip of your finger to the elbow in the 3D space, you also know what this should look like in your 2D projection in an image. And so you can say that if I have a way of measuring a distance between tip of the finger to elbow in this 3D point cloud of a person, I also have a way of measuring it in the pixel space of the image. As long as I can minimize the difference between these two distances, I can still do optimal transport. I can still try to find a coupling that now maps these two different spaces together by trying to keep these two distances as similar as possible to each other. Right, and that's what this Gromov Wasserstein distance ends up looking like. So you have this loss function between the two distances times the coupling of the first point to the first point and the second point to the second point. And that's just another way of showing the same idea. So you do need to have some sense of how to compare groups of points in space 1 and space 2. So you can think about something like multimodal learning, where you have multiple measurements of the same underlying observation, but you know that observations correspond to each other in both modes of measurement. So as long as you know those correspondences, you can do optimal transport. And what ends up happening is that if Wasserstein distance calculation was a linear problem, this ends up being a quadratic problem. So it's non-convex, it's NP hard, it's associated to the quadratic assignment problem, and it's really messed up to solve. But again, Pear et al. Proposed like an entropic relaxation of this problem where you again regularize with respect to the entropy, and you can solve this using Synchrons algorithm again. But now the constraint is that you can solve this generally, but two issues happen. The first is that it's a non-convex problem now. There's no reason that Synchrons algorithm would converge to a local minima or even a stationary point. It might never converge. And the second issue is that you have this really complicated tensor product here between the loss between two distances and the coupling that in general might be quite hard to computationally calculate. But this paper in 2016 showed that if your loss function is of a specific form, which both Euclidean distance and KL divergence satisfy, thankfully, then it can be shown that Synchrons algorithm converges to a stationary point of the non-convex optimization. And this tensor product can be simplified into much simpler calculations. So I won't go into too many details of that, but I just want to put it out there that it is possible to solve for OT between two metric spaces. And this is an example where they're projecting points from a 3D point cloud onto different 3D shapes that have different metrics designed on them, or 2D point clouds instead. So to conclude, I just wanted to say that a lot of this talk has been about developing this idea of optimal transport theory, which is a very rich and rigorous mathematical tool for defining metrics or discrepancy measures between two probability measures. And it's a really nice tool, but in practice, it ends up being very difficult to calculate and doesn't scale well. But a lot of recent work has worked on making this cheap and efficient and actually usable by practitioners in the field. Like you can plug these into deep learning, you can optimize massive neural networks by optimizing some regularized version of these distances. And it has seen a lot of applications in generative modeling, supervised learning, computer vision, and so on. And it's a really nice additional tool to know about and to use. And you can use a lot of these and plug them into your Bayesian inference task or probabilistic modeling task and use these different ideas of metrics versus a regular information divergence. And there's a lot of cool research out there that I didn't have time to cover, but I briefly list here that you're welcome to go and read if you're interested in it. I think I'm out of time, so I'm going to stop there and take any questions if people have them. I see one question in the chat. Oh, yeah. All right, any questions from anyone who's online?
Sorry.
Right. In that case, I'm gonna stop, and yeah, thanks everyone for attending. Hope you took something away from this.
Sorry, can you hear me, Shreyas?
Oh, yeah, I can hear you, Adrian.
Hey, great talk. And sorry, I'm just putting up a few more papers that people may find interesting. So that they've been, I thought you did an excellent job of describing what's going on. I'm just going to put up there's some recent work using using the Synchrons algorithm for work in weakly supervised or even unsupervised contrastive learning, which is another nice application. And also,
I think Adrian's voice was a little low, but he said he's going to link a few works that use the Synchrons algorithm for weakly supervised learning and other tasks. And yeah, definitely check them out. All right.